Hi everyone, welcome to Advent of GPU Code. My name is Jacob Tomlinson. In these videos I'm trying to work through the Advent of Code challenges this year, but writing code that's mostly going to execute on the GPU. I'm doing all of this in Python, so I'm using libraries like QDF and CuPy and Number and that kind of thing. If you want to learn more about kind of what I'm doing and everything, if you have a look at the link down here, there's like an FAQ on in this repo that'll kind of walk you through what my environment's like and everything. But I'm going to jump straight in. I've got my Jupyter Lab set up. I've made myself a new notebook for today, Wednesday the 9th of December, and I've got an empty input file. So let's head over to Advent of Code, and we will have a look at day 9. With your neighbor happily enjoying their video game, you can turn your attention to the open data port on the little screen in the seat in front of you. Though the port is non-standard, you manage to connect it to your computer through a clever use of several paperclips. Upon connection, the port outputs a series of numbers, which are your puzzle input. The data appears to be encrypted with the Exchange Masking Addition System, XMAS, which conveniently for you is an old cipher with an important weakness. XMAS starts by transmitting a preamble of 25 numbers. After that, each number you receive should be the sum of any two of the 25 immediately previous numbers. The two numbers will have different values, and there might be more than one such pair. For example, suppose your preamble consists of the numbers 1 through 25 in a random order. To be valid, the next number must be the sum of two of those numbers. 26 would be a valid next number, as it could be 1 plus 25 or 2 plus 24, etc. 49 would be a valid number because it is the sum of 24 and 25. 100 would not be a valid number. No two of the previous 25 numbers can add up to 100. 50 would also not be valid, although 25 appears in the previous 25 numbers, so two numbers in a pair must be different. Okay. Suppose the 26th number is 45 and the first number, no longer an option as it was seen more than 25 numbers ago, was 20. Now for the next number to be valid, there needs to be some pair of numbers among 1 to 19, 21 to 25 or 45 that adds up to it. 26 would still be a valid next number as 1 plus 25 is still within the previous 25 numbers. 65 would not be valid as no two of the available numbers sum to it. 64 and 66 would both be valid as they the result of 19 plus 45 and 21 plus 45 respectively. Here's a larger example which only considers the previous 5 numbers and has a preamble length of 5. Okay, so here's a bunch of numbers. I'm going to copy my sample here. Let's just have a new file called sample. We'll open that up, put those numbers in. In this example, after the 5 number preamble, which is these numbers 2, 3, 4, 5, almost every number is the sum of two previous numbers. The only number that does not follow that rule is 127. First step of attacking the weakness in the XMAS data is to find the first number in the list after the preamble, which is not the sum of 25 numbers. What is the first number that does not have this property? Okay, so in this example, 127 is this. So this is a rolling window over a list of data where you want to roll over six things, right? Well, you want the preamble length plus 1. So what we could do, we need to write some logic to check, you know, what the, like, how to check whether or not they add up to that. Maybe that'll be a for loop, but our rolling window, we can map over this, right? We have however many numbers in our list. The number of windows that there are will be, you know, the length of the list minus the preamble. And so what I probably want to do from like a GPU point of view is write a function which is going to map over this list. It's going to check each thing individually. You know, each window, it will be checked. And maybe just update an array with like true or false values, and then we want to get the first we'll get the first false from that list. So let's start in here. So let's call this this is day 6. I'm just going to open a previous day just so I can copy and paste code and text and things. So we'll process our input data. So the first thing we want to do is have a NumPy array. So I've been doing this as a function now. So we'll read the data, and this will be the file name. And we'll do with open file name as a what's called a fh file handle, and then we'll have our data equals fh.read lines. This is just a 1D array, right? So actually, probably what we want to do is do line for line in fh.read lines. We need to call strip on here, so that we take off at like the trailing new line. These are all integers, so we want to cast that to an integer, and then we should import NumPy as np, and we'll do np.asArray on our input data here, and then we want to return data. So if we have our sample input is going to be read data of sample. Let's have a look at it. Okay, our sample input is an array of these numbers, which is great. That's fine. That's what we want. So now we want to start solving part 1. So let's do part 1. What we first need to do is let's just put in some scaffolding for our GPU function, which I tend to do like this. So I need to do from number import CUDA, and we'll make ourselves a CUDA function, and just copy these pieces here. I seem to be following this pattern every time, right, where I'm doing this kind of thing. I'm just going to pass like that, and then we have to calculate our threads per block and blocks per grid, and then we want to do something like this, right? So we've been doing the same pattern over and over through Advent of Code since reasonably early on, where we have a CUDA kernel here, right, which is a Python function that gets run on the GPU. It takes in some inputs, and it also takes in an output, because we can't return anything from CUDA kernels. So we have to have like an output array to put things into. So we take in some things, and then we work out, like a CUDA kernel, you can work out which thread you are in the grand scheme of things, like getting the position from CUDA.grid. This gives you like an absolute position, and then we can just say, well, we might have launched more threads than we have data, because threads have to be like a round number. So if your thread number is like bigger than the input array, then we just won't do anything. But if you're not, if you are in the input array, then we should do some work. The next thing then we have to do is we need to say, well, we're going to do 128 threads per block, just because that's a reasonable number of threads to run in a block. And then our blocks per grid, right? Our grid is our like total. How many threads in total do we want? So how many blocks do we want? Of how many blocks of 128? So this will be, you know, the length of our array basically. So I mean, this is going to be trivial. We're going to have like one block here. So let's have our sample input. I'm going to rename this actually. I'm just going to call this what is it? What is the actual thing? Transmission? Let's call it transmission. Transmission. Like that. Right, so we're going to take in our transmission. We're going to take in an output array, and then length of transmission, and then here the length of transmission. So I'm just going to pass. But what I have actually been doing is doing output position equals 1, or maybe even position, which is fun. So you can see we have our output array. We'll come to this in a second, but we're updating this thread, if this is thread 0, it will update output 0 with the position of it. And then it's sometimes useful to see here, we have one block here because there's only how many items in here. 128 threads is gonna kill working over this thing, but those threads are going to run at the same time because it's the GPU. That's fine. Let's get rid of that. So then the next thing we want to do is create an output array full of zeros. It's just another NumPy array of zeros, but we want it to have the same length as the number of times we want to go through this. Now I'm just going to do a 1-for-1 at the moment, but we don't actually do a 1-to-1. Want to do a 1-for-1 because we're going to do a rolling window, right? And this is going to be validate number. Yeah, let's call this validate number. Validate number. So that'd be here. We're taking our blocks per grid and everything. It takes the transmission and our output and then return, and then just shows us the output. So if we run this now, oh, I need to run that again to redefine it. If I run this, well, you saw my GPU dashboard did a little bit of work just for a very brief second there, and you can see our output array has been filled with our thread positions. So it started as an array of zeros, but it's finished as an array of out positions. Whereas I've got a slight cold, so I apologize if there's any coldy sounds. What I want to do here is actually make this more of like a Boolean array or a ones and zeros kind of thing. But what we need to do is we're going to roll over transition. Let's define ourselves like a constant here of preamble length. Is that what it said? 5 number preamble. So let's go preamble length is 5. So we've got this preamble length. So what we actually want to do is, we're going to have the first window needs to be 1, 2, 3, 4, 5 for our preamble, and then 6 for our number, right? Because we want to check if 40 is the sum of one of these. And then the next one is going to be this window here of 5 items, and we're going to check this one. All right, so we've got 2, 3, 4, 5, etc. Right? So our total number of windows is going to be the length of this minus 5 because we have a preamble of 5. We don't care about the first 5. So actually, we don't want to do length of transmission. We want to do length of transmission minus the preamble length. And this needs to be length of transmission minus the preamble length. And this needs to be length of transmission minus the preamble length. I can define that as a variable somewhere, right? But actually, we only need 14 executions to roll over our... I haven't actually done the length of transmission, so you can see what it is. So here, 20. I only need to do 14, like 0 through 14, right? So we can do 15 windows. Will take us over our 20 items because you need the 5 either side. So the next thing we want to do is say for all of the items in our we want our little array, right? We want like a slice. So our preamble here is going to be our position. But it's going to be transmission at position, right? This will be our starting position to position plus 5, right? Oh, is it plus 6? Plus 6. That should give us 6 items. No, it's plus 5 because that's our preamble. 5. And then we also want our... I don't know what to call this thing. They're just calling it a number, isn't it? Valid next number is going to be our transmission position plus 6, right? Yeah, so let's do that. So then we need to say we want to we need to add all of these numbers. We need to do like an all-to-all add of these, and then see whether the next number is in that, basically, don't we? But let's just do, wonder if there is a numpy function for this, and whether we support this here. But numpy add all numbers to all numbers. Sum one number to every element in a list. Yeah. But it doesn't count if it's the same number, right? So, no, I don't want sums of columns or rows. I want, or maybe no, I don't think I want to do that either. Maybe I just do for I in length of in range 5, and then 4. I almost want, this is going to be zeros, right? And for j in range 5, if I is j, if I is not j, and then if I plus j equals next number, then output position is going to be 1. Let's just do that, right? So we can have zeros, but we're going to try them together, and if we find these things, and so we want if I is not j, and no, it's going to be preamble I plus preamble j, and then here if and that doesn't equal that. Let's try running that. Okay, so we get a bunch of ones, and then a 0, and then some more ones, and then a 0, right? So we've mapped over the whole lot of windows. I come out with these things. I think actually this is a misnomer, because it's not minus preamble length, it's plus 1 as well. Minus 1. I don't remember which order these are in, right? It's the length of the transmission. The preamble length is going to be 5 plus 1. Let's just do that, right? Or maybe it should be called window size is 5 preamble plus 1 thing, right? So window size. Let's do that. Instead of that, we're gonna have window size. Okay, so there's one item in here, which is this. And then let's do like numpy get first occurrence. Find the index of the first occurrence. How does that work in numpy.where? Okay, so we can do np.where output is equal to 0, which will give us that. And then we want the first one of those. No, it needs to be like that, right? So that is the index 8. And then it said the only number that does not follow the rule is 127. And then it says which, find the first number in the list. So we don't want the index, we want the actual number. So this will be transmission of that index, right? It's not. That's interesting. Yes, it will be that plus the window size. Or is it going to be plus the preamble size? No, it is plus the window size, 127. Yes, that makes sense. Because we're counting from, you know, the thread with 127 in was actually 1, 2, 3, 4, 5, right? It was 95s. 95 was like the start of the window, right? So we actually want to grab the item from the end of the window. But that makes sense. I'm happy with that. So we've got 127. So what we actually want to do now is take our full puzzle input like this, and we'll put this into input. Oh, that's a different input. Our new input here. Ooh, these numbers get big. Okay, we've got 1,000 numbers. Now transmission is going to equal our input. Okay, which actually now looks like this. Pretty big. I'm going to not print that. We've got our transmission, which is 1,000 items. Our window size is still the same. We're going to do the same code. Let's see how many blocks we're going to run now. Instead of running 1 block, we're going to do 8 blocks, right? So there's very little extra going on here in terms of the GPU. It's only doing 8 times as much work. Now if I run this and get our output, oh, that's interesting. So 20, it's saying, is there a different? It's 25. Our preamble is 25 in this bigger thing. That is why. So our window size is now 25 plus 1. And so, yeah, that should be fine. So let's try doing this again. It's still not giving me what I would expect, actually. This worked for our small. I'm going to restart just to make sure I haven't messed up my base or something. So let's get our window size is 25 plus 1. Do this. It's got our window size. There we go. This would be y. Window size minus 1, and that'll be plus window size. And then these ranges are of our window size minus 1. No, actually, I'm gonna have a new constant as well called preamble size equals 25, and then we'll make this preamble size like that. So our window, yeah, that's our window size. That's our preamble size. That's our window size. That's going to be our preamble size. That's going to be our preamble size. Yeah. Okay, let's try doing this again. Okay, that's better. Lots more ones. And so we've got a 0 here. So let's do this. Saying the answer is 84. 84. That's not the right answer. Oh, that's a shame. Okay, back to day 9. Right, where am I going wrong here? So I'm going to restart again just to make sure I'm getting a consistent answer out here. 84. And let's just, for sanity, check our sample, which has got a preamble of 5. And see if we still get 127. Yes, okay. Our code works for our sample, but not for our input. Let's see if I've missed something. Two numbers will have different values, and there might be more than one such pair. For example, suppose your preamble consists of the numbers 1 through 25 in a random order. To be valid, the next number must be a sum of 2 of those numbers. 26 would be a valid next number, as it would be 1 plus 25. 49 would be a valid next number because it's 24 plus 25. 100 would not be valid. No 2 of them add up to 100. 50 would also not be valid, although 25 appears in the previous 25 numbers. The 2 numbers in the pair must be different. Just curious, right? The preamble consists of the numbers 1 through 25 in a random order. To be valid, the next number must be a sum of any 2. 26 would be valid for loads of reasons. 49 would be valid. 100 would be valid. 50 would also not be valid, although 25 appears in the previous 25. the two numbers in the pair must be different. It only appears once anyway, so I don't think that's like a... I don't think that's like a thing, is it? Like, suppose the 26 number is 45, and the first number, which is no longer an option. Oh, interesting. As it's more than 25 numbers ago. So the new number is... But maybe our window size is actually going to be like this. Windows, preamble size. Let's just go back to our sample and see if that changes anything. Yeah, it does. Oh yeah, that should be preamble size. 127, okay. I wonder if I've just read this wrong in that I assumed it would be 25 numbers and then you have your next number, but actually I think the next number is... Oh, and it's only the previous numbers that we care about, so we're stepping over... No, I'm confused. I'm slightly confused. So I'm expecting you have, you know, 25 numbers and then your new number, right? And so you care about these independently. But maybe not. Let's just try changing this to input. I'm gonna do a bit of a... Okay, it's giving us this as an answer. Just curious to see what happens. But that's the right answer. Okay. I get what happened there, but I don't think that was not quite clear, because it was kind of saying, oh, the previous 25 numbers, but that's including this number. Anyway, continue to part 2. Maybe I'm just doing indexing wrong. Part 2. The final step in breaking the Xmas encryption relies on the invalid number you just found. You must find a contiguous set of at least 2 numbers in your list which sum to the invalid number from step 1. Again, consider the above example. In this list, adding up all of the numbers from 15 through 40, produces the invalid number from step 1, 127. Of course, the contiguous set of numbers in your list might be much longer. Okay, but it's a contiguous set. To find the encryption weakness, add together the smallest and largest number in this contiguous range. In this example, there are 15 and 47, producing 62. Okay. So 15 through 40, those 3 numbers there add up to 127. So let's think about this. What we need to do is step over our array again. That's fine, right? Let's just put part 2 header here. Part 2. What I want to do now is I want to step over every start point, every number. And we have our input number, right, which is here. This is our... Let's do this with our sample again, actually. Let's just take our... we have our sample transmission. Maybe I should put this up here. We have our sample transmission. Yeah. Just sample. We don't care about our preamble size this time, but we know 127 is the answer to the last output, so let's have a new constant here, which we will call our target number. let's make it 127 for now. And then let's write a new, let's think about this logic. So what we want to do is go over each of these numbers. So starting from here, 35, we want to add it to the next one and see whether or not if it's smaller than our target, then add another one. And if it's still smaller than our target, then add another one. And if then it gets bigger than our target, move on. But then if we add them together and it's equal to the target, then we should return a 0 or something. So we want to step over everything this time. Let's have a new function here, and we'll calculate these things again. And we'll run it again. So this time what we're doing is we're searching for contiguous numbers, right? Let's call this like contiguous search or something. Contiguous search. Okay, so contiguous search like this. We've got our target number. Let's just get rid of all of this. So we are gonna go through the length of transmission. Get rid of all of that. Unless we're just going to go through the whole length of the transmission. And yeah, our output is going to be the length of the transmission. Then our contiguous search is going to take the transmission and the output. And let's just do, again, I just like to do this to make sure I've written this code properly. Let's just do this. So we're going to go like that, and we should see our output array is 1,000 items. Yes, because I think we want to just put in our sample transmission here for now. Sample transmission and sample transmission here. Okay, so this is our short thing. Now what we want to do is it's going to be zeros, and we want to do if transmission, we want like a accumulator or something, right? So we have ACK equals, no, we'll start with transmission position, and we'll say ACK, yeah, and then we say if transmission position what if we want to do something like while ACK is less than our target number, and then we'll do ACK equals transmission position. Let's have a counter as well. Counter equals 0. We want to do like a sum on our transmission position to position plus counter, right? Yeah, that makes sense, doesn't it? We're going to keep adding our next numbers, and then we'll do counter plus equals 1, counter plus equals 1. And we'll say, well, that is less than target number, and counter plus position is less than length of transmission, right? So we don't go off the edge. Transmission. We're going to do that. Got our accumulator, and then we want to say if ACK equals our target number, yeah, that makes sense, I think. If that equals that, then we'll set this to 1. So we're going to go through each number, and then yeah, each start point, and we've got that number and a counter, and then we're going to say while this is less than, we can probably start the counter from 1. Anyway, while this is less than our target number and we're still in the list, we haven't gone off the edge of the list, then we're going to add together our like a slice of our list, right, starting from the position. So we'll add together 2 elements and then 3 elements and then 4 elements or whatever in our list. I'm going to keep doing that. We're going to keep incrementing our counter, and then if they are equal, we're going to do that. I think that looks right. Typing error, great. Failed. Global name sum cannot be used, cannot determine number type of class. Okay. What if I can do mp.sum on that instead? No. Unsupported function numpy sum or unsupported user function. Okay. This is a slice, right? This is our slice. Oh, I shouldn't use the word slice, but our slice. We want to add all of those numbers together, right? Which if I want to do something like for n in that is not really what I want to do. Mp ac equals 0 for n in that list, ac plus equals n. Okay, that worked. That's a shame, but it worked. Okay. This feels a bit weird that we can't use sum to do that same kind of thing, but we've written our own sum. That doesn't really matter. So the numbers 15 through 40 produce the invalid number 127. So 15 is the third item there, and our flag here is in the third item, which makes sense. So now what we want to do is actually, instead of setting this to 1, we want to set it to our number plus the end number, right? Which is 15 and 40. Smallest and largest numbers. These are 15 and 40. Ah, yes. Okay. The smallest and largest numbers. So actually what we want to do is say can I do min and max here? I want to do output equals min of that plus max of that. Will it let me do that? Not implemented error. Right, I don't know what that's saying, but I'm guessing we can't do that. So what actually we need to be doing is tracking our min equals zero and our max equals 0. And let's call it n min, n max, n max. We're going to do for n in, actually that needs to go in here, right? And then we'll say if n min is 0 or n is less than n min equals n, and n max. It's going to be the same logic, right? But if it's 0 or n is greater than n max, then n max is going to be that. And then our output is going to be our n min plus n max. Oh, what have I done wrong there? Oh yeah, that's silly. Okay, 62, which is our answer here, 62. Excellent. Okay. this has involved a little bit of implementing, right? I haven't been able to use sum or min or max as like built-in Python functions that I would normally use. I've had to kind of track these things myself, given that I'm doing this on the GPU, but it means that we've worked through this. So now what I should be able to do is, and we probably want like a np.where output, np.where output is not 0. Oh yeah, that'll be output 0 0. Well done, miss my brackets. 62, and it's an int because it's expecting int. So yes, right, that's given us our answer then. So now let's do the same thing, but for our regular transmission, and then go like that. 58. That doesn't seem right. I think that is maybe because how many blocks per grid have we got going on here? 8. Okay. I don't think it was 58, or would be 58, would it? Seems very small. Oh, it's because our target number is wrong. That's what it is. Panic over. Our target number is this number here. Target number. Oh, it's because I need to redefine that with our target number. Yay. Oh, that made the GPU do something for a second. It's exciting. So now if I submit that, that's the right answer. Fantastic. Success. Okay. Lovely. This notebook maybe needs a little tidying just because it does. Maybe I'll pass this in, this target number. Target here. We'll pass in target number like that, which will give us 62. Let's move that up into there, just make that neater. And then our target number here is now changed, and we're going to put that in there. I've done something wrong. Let's restart. I just want to make sure that my notebook actually runs end to end. Do that with an output. 62. Let's give me 58 again. What have I done? I might just delete our sample test here. We'll just go like that. Okay, I'm not quite sure what's going on, but anyway, we've got our parts that we're working through here, and we've got the right answer. So that was it. I hope that was a useful kind of view at how we can do like a rolling window in Number CUDA like this, and kind of work through and find our outputs. I might just copy this as well and put that there just to make that look more pleasant. But yes, thank you very much for watching, and I will see you next time.